Hello 4A class. What I wanted to do is cover a new material called Work and Energy right here. We'll actually spend the next two assignments on this topic right here. Now, first of all, I should tell you that this work and energy is just a consequence of Newton's laws. We can derive all this just from Newton's laws right here. So every problem we did with Newton's laws, we could do it with work and energy. You might say, why do it with work and energy? Because work and energy makes problem solving easier right here. You might say, why didn't we just learn this at the beginning? Well, you wouldn't have appreciated it. Okay, so now let's go ahead and let's define what work is. The definition of work is defined as F dotted with S. S is the distance that the object moves. It has a direction and a magnitude. F is the force acting on it right here. I should tell you that this definition is really only good when the angle between those two is constant and the force is a constant. But all of our problems so far have been that way. This will work for all the problems that we'll have right here. The units are force times a distance is a Newton meter, and they just call that a joule right there. So just to remind you of the dot product, we had two equations for the dot product, but the one we'll be using mostly is just A dot B is the magnitude of A, magnitude of B times the cosine of the angle between A and B. So it'd be the angle between F and S. So here, let's just say we push on this block right here with this red force right here. And it's going to move from here to here. So S is that vector. It has a magnitude of D, and the direction is that way. So when we do the dot product, F dot S, it's the magnitude of F, magnitude of S, which is going to be D, times the cosine of the angle between that way and S. So it's just theta. So it's the cosine of theta right here. So that's how much work it took to move this over to here. You'll notice right here, if theta would have been pushing straight down, then the angle would have been 90 degrees and you wouldn't be doing any work right here because at least that force wouldn't be in moving it from here to here. If you pushed it this way, where theta was 0, then this is a maximum and you're doing maximum amount of work. So just remember the dot product, what this dot product really means, it means the component of force in the direction you're moving times the distance you move it. So this thing really gives me the amount of force that way, which is F cosine theta times the distance it moved. So we could do all the work just by lifting a book. Suppose you have a book. It's on the floor. And all of a sudden you just lift it up, put it on the table, and you ask, how much work did it take for me to lift that up? We'll lift it up at a nice constant speed so that, what does that mean? That means that the force I have to apply, that P force, and the mg are equal. You're in equilibrium right here. So the work would be the force, which would be P or mg, times the distance, which is h, times the angle between them, or the angle between this and these two is 0. Cosine of 0 is 1. So the work it takes to lift that up would be P times h. P is mg, so there's how much work it took for me to lift the book up onto the table. Now, we know for every action there's an equal and opposite reaction, so if I wanted to find the force, the work on my hand, remember the book applies an equal and opposite P force back on my hand, and since it's in the opposite direction, the angle would be 180, cosine of 180 is negative, so the work on my hand would be minus mgh right here. And since for every action there's always an equal and opposite reaction, anytime you do work on something, it's going to do a negative amount back on you. So let's just say this was 20 joules to lift this thing up. The book gained 20 joules. I lost 20 joules right here, which means that whenever you do work, you're shifting something from one object to another. What are we shifting? Well, we call this quantity that's being shifted energy. You can't see it, but we call it energy. So I lost 20, well, if this was 20 joules, I lost 20 joules and the book gained 20 joules. but the total amount of energy stays the same right here. So we now say that book sitting up there has potential energy. It could potentially fall off the table, hit a crank, turn a generator, light a light bulb. So everything that's above the ground must have some sort of potential energy because it could potentially fall right here. And it looks like it'd just be mgh right here. So work is just the transfer of energy. And since you can never create or destroy energy, we say it's conserved, it makes problems easy because all we have to do is keep track of it right here. If we just keep track of all of our energy, then we know what's going on right here. So let's just look at a case where we have a block and we have the two blocks right here. Let's say they're in red first. They're tied together with a rope. And then you let it go. And a little while later, it's over here. So these two blocks are just shifting right here. It's the same system, right? It starts here and it goes to here. Suppose we wanted to find the work due to each one of those forces. You notice there's a lot of forces. You have an mg, we got a friction, we got a normal, we got a tension on that one. Over here we got a weight, we got a normal, and we got a friction on that one. So suppose we wanted to calculate how many forces. We got 1, 2, 3, 4, 5, 6, 7, 8 forces. So we have 8 works right here. Well, let's first look at the work due to this M1G. The work due to M1G would be M1G dotted with S. Remember, S is this way, M1G is that way. It's 0. Why? Because you're perpendicular. Cosine of 90 is 0. The work due to the normal, this normal right here, N dotted with S, that's also 0. It's perpendicular. Any force perpendicular to the way you're moving, you don't even need to bother with it. The work due to this tension is in the same direction you're moving, so the angle is 0, so it's just T times D. The friction is opposite the way you're going, so the angle is 180, cosine of 180 is minus 1. So there's the work due to the frictional force. Now, if we come over to this block right here, the work due to the weight, mg is this way, s is that way, so we got mg dotted with s, so we got m2g times the distance, which is d, we're calling that distance d, times the angle between here and there. Well, that angle between here and here, remember this angle was theta, we already did that from before, so the angle from here the rest of the way would be 90 minus theta. So we got the cosine of 90 minus theta. And we know the cosine of 90 minus theta, right there, is just sine of theta, right there. This is just sine of theta. So this is just m2gd sine theta. Okay, well, we can find the work due to N2. N2 is perpendicular, so that's 0. We can find the work due to the tension. That's T. S is this way. Again, 180 degrees difference, so it's a minus TD. And the friction, this way, you're moving that way, it's 180 degrees, so it's minus frictional force times D. So there's all the works due to all these 8 forces. Normally, we're not going to do all this. We're going to have an easy way of doing it, but I just wanted to show you how you could get the work due to all these. Now, what we want to do is, when we looked at forces, we looked at one object at a time. When we look at work and energy, we want to look at the whole system right here. So suppose we were to add up all the works to get the total work right here. Well, if we add up the total work, first of all, you notice the normal, work due to normals are always 0. They're always going to be 0 right here. Why? They're always perpendicular to the way you're moving right here. And even if we had a couple of problems where they were in the same direction when we had horizontal normal forces, but when you looked at the other object, that was going to always cancel itself out. So we never have to deal with the work due to the normal. The tensions right here, you notice this tension is TD, that one is minus TD. If we look at the entire system, they're always going to cancel. You notice this tension is helping this block move. This tension is slowing this block down. They're always going to do equal and opposite amounts. So we never even have to worry about ropes anymore, the tensions. So that makes life a lot easier. We don't have to, this is always going to be true as long as we look at the entire system. So in our system right here, the only ones we have, when we add up all of these, the only ones we have are these two negatives and this one positive. You notice if it's positive, this was helping speed it up. These are helping to slow it down. So anytime the work from a force is positive, it's probably helping it speed up. Anytime it's negative, it's always going to slow down right here. Now on the next sheet right here, we'll go through what does this total work tell me right here. What is the total work right here? So we'll have one, eventually we want to work out till we just have one equation that will be used to solve everything. Okay, and we'll start going through that next time.